Hello, and in this video we're going to have a look at how to conduct the analysis of covariance in SPSS. Now, I know I've done previous videos focusing on R and SAS, but I'm going back to SPSS for this video because it's a little conceptually more complicated, so I wanted an easy point-and-click interface that lots of people will be familiar with that I can use to explain the concepts before we go on to show you how to do it in syntax in R and SAS. Now, analysis of covariance is, or the ANCOVA, is a variant of the analysis of variance that we've looked at previously. It's just an analysis of variance where a covariate has been included. Now, this is conceptually a very hotly contested technique because it's misunderstood by a lot of people and misused by a lot of people. Some experts have even said that the technique shouldn't be used at all because even conceptually it's entirely flawed. Now, we're gonna go over this technique anyway because it's taught on a lot of undergraduate psychology courses. So I think it's valuable to teach, but just bear that in mind. So what is an ANCOVA? What is a covariate? Well, a normal ANOVA we use to look at the differences between two or more groups on one continuous dependent variable. Well, an ANCOVA and we're just going to be looking at ANCOVA with one independent variable this time, but like ANOVA we can use more than one independent variable. But ANCOVA has two explanations. One, the conceptually simple explanation, and the kind of attractive explanation in terms of research is that we can use ANCOVA to look at the effects of a manipulation after controlling for the effects of one or more covariates. Now, let's talk about why that's both conceptually and statistically not the case. Firstly, I don't care how advanced of a statistician you are or what procedure you use, but no procedure can truly control for effects that weren't controlled experimentally. There's no way you can know for sure that even if you measure a confound and try and estimate what the effect of that is, there's no way you can be sure that a certain confound didn't have an effect unless you control for it experimentally. So saying control for is conceptually flawed. At the very least, if we're gonna make that argument, what we should be saying is that we're adjusting for the effect of the covariate. We're trying to estimate what influence it's had and trying to statistically estimate what would have been, but we can never say we've removed the effect entirely and we just have means as if the effect was never there. So it's flawed conceptually. It's also flawed statistically in that it's an assumption of the ANOVA or an assumption of the ANCOVA that the groups that we're using are actually equal on a covariate. Now, so we can't be controlling for differences on the covariate because if they're supposed to be the same on the covariate, then that obviously isn't gonna happen. What in terms of why this is a problem? A lot of people, for example, one of my lecturers does a lot of studies looking at the memory performance, and he compares smokers and non-smokers on memory performance, and what he wants to look at is the effect of smoking, but alcohol may also have an effect, so he compares smokers and non-smokers while using a covariate of the amount of alcohol consumption they use. That violates an assumption of the ANCOVA in that our covariate and our experimental effect must be independent. That means we can't have in that example that I just gave, it's highly likely that smokers also drink more alcohol than non-smokers. So our experimental effect is also confounded with the effect of the covariance. So we should only be really using ANCOVA when we have randomly assigned participants to conditions, so that there shouldn't be hopefully different on a covariate, and there's no dependency of the experimental effect on the covariate. So with all that said, what's ANCOVA for? If we're not controlling for differences between people on something, then what are we doing? Well, if we remember back to the ANOVA videos, ANOVA has in a basic sense works on the ratio of what our model can explain to what our model can't explain, and we're saying some of the variability, not between the groups but within individuals, can be explained by the effect of our covariate. So we're reducing the error in our model, and as the what our model can explain gets divided by what our model can't explain, if what we divide it by is getting smaller, then our resulting F ratio and our significance values are going to be lower. So we're essentially giving our analysis more power and making it easier for the effect to be significant. So ANCOVA isn't about controlling for differences between groups, because it's an assumption that the groups are the same on the covariate, but rather what it's about is using the covariate to reduce some of the individual uncertainty in our model. So with that said, let's take a look at an example. I've got SPSS document open here with the data we're going to use for analysis, and like I said, in this case we've just got two groups and one covariate, but we could have multiple groups and multiple independent variables and multiple covariates. So the idea of this fictitious study was we wanted to see if seeing just cross-examination of a witness and then seeing just cross-examination of a witness resulted in lower credibility than seeing cross-examination and then the original counsel be able to clean up what happened on cross-examination, whether that would result in higher or lower ratings of their credibility. But because in the cross-examination that we subjected people to was cross-examination by the prosecution, it's entirely possible that how anti-law you are might explain some of the variance in the credibility ratings you give. I should say that this is a fictitious study, so we showed them the examination of their respective condition, and asked them to rate the credibility of the witness out of 20, and also asked them out of 10 for a rating of their anti-law enforcement attitudes. So we're hoping that their anti-law enforcement attitudes can explain some of the variance in their ratings and give us some more sensitive analysis to decide whether there is a difference between just seeing a witness cross-examined versus seeing the witness cross-examined and then the defence have an opportunity to come back and rehabilitate the credibility of the witness. So that brings up an interesting point. In this fictitious study, we measured their anti-law enforcement attitudes before we did the experiment, because if we want our covariate and our experimental effect to be independent, which we do, then we can't have our measure the covariate after we do our experimental manipulation, because our experimental manipulation might affect the dependent variable like we want, but it might also affect the covariate. So we'll measure that first. So let's first do you wouldn't usually do exploratory analysis like this, because you'd usually decide what analysis you were doing and then go ahead and do it. But for demonstration purposes and for something I'm going to talk about later, let's do a usual one-way ANOVA just with no covariates to see if there is a difference between these groups. So to do that, we're going to analyse general linear model univariate, and we're going to put our dependent variable in as our dependent variable, and we're going to put our independent variable in the fixed factor box. For now we're going to leave out the covariate, because we want to, like I said, we want to compare what the effect is without the covariate versus with the covariate. So with that, I'm just going to click OK, and we get some output. And for the effect of our independent variable, it's 0.064, so it's just more than 0.05, so not quite significant. The important things to bear in mind here is that what we're looking at here is our mean square for our experimental effect divided by our mean square error. So if we can reduce the error in our analysis, then hopefully we can get a higher F value and give us a bit more power to detect a significant difference if one does exist. So that's the theory of ANCOVA. But before we actually just go and add a covariate in there and do our ANCOVA, there are a couple of things we need to check. ANCOVA has all the same assumptions as ANOVA, but it also has an assumption called homogeneity of regression slopes. And that means that because obviously our covariate has to have a relationship with our dependent variable, otherwise we're not gonna it's not gonna explain any of the variance in it. It's just gonna add in more error and make things worse. So not only do our covariate and our dependent variable have to have a linear relationship, but that linear relationship also has to be the same across all our groups, because as we'll see later, ANCOVA only estimates one effect of the covariate and makes one correction for the covariate. It doesn't make separate corrections for each of our groups. So if we're making the same correction for all groups for the covariate, but the relationship between the covariate and the outcome is different in our different groups, then just intuitively, assuming the same relationship when we know it doesn't exist is not going to give us an accurate analysis. So how do we test homogeneity of regression assumption? Well, we can test it graphically first by drawing a line chart. So to do that, we're going to go graphs, chart builder. I've already defined all my variables, and we're going to ask for a scatter plot, but with different colours for different groups, so we can see how the relationship differs. So I'm going to drag that in. And remember, what we want to look at is the relationship between our covariate and our dependent variable. So put the covariate on the y-axis and the dependent variable on the y-axis and the covariate on the x-axis. and what we want to split our groups by, the two different relationships we want to see are reflected in our inclusion of redirect examination variable. So I'm just going to put that in our different colours. If we hit OK, we should get some output. And the relationships look similar here, but it's a bit difficult to see what the general trend is. So if we click on our graph, we can ask for fit lines at subgroups, and this is gonna make us a regression line for each of our groups. So if we look at this, we can see that the line is positive in both groups. It's a little steeper in the group that saw defense redirect than the group that didn't, but it doesn't look, if we look at these slopes here, the slope of these lines, it doesn't look like much of a difference. And actually thinking about this in a regression context is going to be important later when we look more at why this homogeneity regression assumption is theoretically important. And we've looked at this kind of graphically, and we've said there isn't much difference between the slopes, but we're just like why we can't just interpret a difference between our two means just by looking at the raw means. We need some kind of measure of significance, and to measure that significance, what we want to quantify is the interaction between the effect of our covariate and the effect of our group in predicting the dependent variable. If there's an interaction between the covariate and the group, it means the slope or the effect of our covariate is significantly different between our groups, and that's what we don't want. So how do we test for that? Well, we're going to go ahead and run our ANOVA again. Analyze, general linear model, univariate, and this time we're going to put our covariate in as our covariate, but we don't want to do the ANCOVA yet because we need to check this homogeneity of regression assumptions. So we're going to say that's what we want, but then we're going to customize our model, and instead of leaving it as the default, which is ANCOVA in this case, because we've had in a covariate, we're going to say custom, and it's going to allow us to specify the effects that we want in our model. Well, what we want is the interaction between our covariate and our outcome to see whether that's significant or not. And now we could just add in the interaction in itself, but we don't want to do that, because if we don't add in our covariate and our outcome, then obviously some of the variance that's explained by the covariate in the outcome would be explained by the interaction. So we want to see if the interaction can explain anything over and above the effect of our covariates. So over and above the effect of each of our variables. So to do that, we're just going to drag both our variables individually across. So because we put the main effects of our group variable and our covariate, no variance will get misattributed to the interaction that isn't really due to the interaction, but rather is to do with everyone else's effects. But we did that just to make sure the effect we're actually interested in is our interaction. So we've already got build term on interaction here. So if we select both of our variables and press the arrow, we'll get the interaction between our covariate and our dependent variable. So That's what we want. So we're just going to hit continue and hit OK. As was borne out by the graphs, we see we get a p-value here of 0.137. That's a lot bigger than 0.05, and so it's a non-significant effect. So what this is saying, in reference to our graphs, is that that difference that we see in slopes, the fact that one's steeper than the other, is not significant. So it's okay to assume that our relationship was the same. Hence the homogeneity of regression assumption, homo meaning same. So we can now go ahead and do our ANCOVA. So in order to do that, we're going to go back to our analyze general linear model univariate, and we've already got our effects specified errors we want, because dependent variable is credibility rating, our independent variable is whether this will redirect or not, and our covariate is anti-law enforcement attitudes. But we customize the model, so we need to do it to say we want you to actually do an ANCOVA now, as you would by default. We don't want this test under homogeneity regression assumption, so to do that we're just going to move it back to full factorial, hit continue. And that'll give us an ANCOVA, but there are a couple of other things we want to be able to interpret our ANCOVA. We can get most of those from the options tab. First of all, we see this estimated marginal means option, and the estimated marginal means are the means that were estimated by the model. Now, as we'll see later, ANCOVA uses a regression type structure to estimate what the effect of the covariate was, and then adjust the means of our different groups to take account of that effect of the covariate. Now, it's important again to realise that we're not making the groups equal on the covariate, but by reducing some of the variance within the individual people, then obviously the overall means are going to change slightly. So to get the means that actually apply to the ANCOVA, we might usually click on descriptive statistics here. That's going to give us the means that were estimated in our sample, but the means that are actually compared by the significance test are the ones that were given to us by the regression model. So we want those, and we're going to drag them over here. Now, because I want to illustrate the difference, we're going to leave descriptive statistics on, but the estimated marginal means are the ones we want to compare. Now, we can't do regular post-hoc tests through the post-hoc option on an ANCOVA. Actually, if we look, our post-hoc option has been grayed out. You can't do just regular post-hoc tests on the estimated marginal means, but if you've got more than two groups, a covariate that you're adjusting for, you still need to have some way of knowing if there's a difference between your groups. So that's what this compare main effects option is for, because there are some simpler post-hoc tests that let you to do mainly a Bonferroni and a SIDAC, but we're not using this in this case, because if we have a significant effect on our ANCOVA, then the only couple differences between are the no redirect and the redirect group. But I just wanted to show you that, because if you had more than two groups, you might wonder where you would get post-hoc tests from. So we want our estimated marginal means descriptive statistics. We also want homogeneity tests like ANOVA. ANCOVA assumes that our error variances are homogeneous across groups, and we also want the residual plot, because ANCOVA again assumes that our residuals are normally distributed and there's constant variance in the residuals. So we're going to hit continue and hit OK. First of all, we see that our Levene's test is not significant, so we can go ahead and assume the homogeneity variance assumption. We get our descriptive statistics. Again, these are the descriptive statistics that you'd get for calculating any mean, not from the regression, and we'll compare those to some means and means that we'll see later. Right below that, there we've got our ANCOVA, and we see that when we pooled our estimate, our covariate had a very significant effect on our outcome, and after we use that covariate to explain extra variance in the outcome, the effective group now became significant. Now, if we see what this is doing, you can see here we've got our experimental effect had a mean square of 111 units, and there were 3.993 units of error. If we go back to our experimental effect, our regular ANOVA, we see that there's about 10 times more error, and our experimental effect is about the same size. So if there's more error, then obviously our F value is going to be smaller, but we've reduced the error. So that's what ANCOVA is good for. Now, let's stress briefly why there is a bit of a difference in the mean of our the mean square of our experimental effect. I said the ANCOVA isn't about controlling for differences between groups, about making our groups different. It's about reducing error, but our errors become about 10 times smaller. But if we look, our experimental effect has also changed slightly. Here it was 102.4, and if we look at ANCOVA, it was 111. Why is that? Well, that's because if we look in this next box, our means have become slightly different. One's gone from 8.6 to 8.45, and the others increased slightly. So, overall, adjusting our individual scores has adjusted our means slightly, but that's not. So that's why we get a little bit of a difference. But say, theoretically, it's about reducing error variance, and then we get our residual prop. Probably not exactly what we would want to meet this assumption, but we're just doing this for demonstration purposes. So there you go, we've done our ANCOVA, but I want to go into a little more conceptually about what the ANCOVA is doing, so you understand the point of the homogeneity of regression assumption, why it's important that when we pull those relationships to estimate one effect of our covariate, why is it important that our groups are the same on the covariate, and why we're not controlling for differences on the covariate. To understand a little more about what ANCOVA is actually doing behind the scenes, we can look at it within regression framework. So, which regression estimates the relationship between how much variance can be estimated by a predictor in our outcome variable. So, how in this case we can use how much we can use the group that someone's in to predict what credibility rating they're going to give, or in this case, because we're looking at two groups, what the mean of the credibility rating they're going to give. So if we think about ANCOVA within that framework, what we're doing with ANCOVA is saying we've got this additional predictor, the covariate, that we want to see if ANCOVA can explain the covariate, if the grouping variable can explain anything after we've taken this covariate into account. So let's add that in. Let's do that. So we're going to go analyze regression and linear. The thing we want to look into is credibility rating. That's our dependent variable, and our predictors, or the independents as this calls them, our independent variable and our covariate. Now, if we put these in as one block, it would work, because if you have only two predictors, the individual significance tests are gonna tell you no matter what order you put them in. If you put them in the same block, but a lot of people, when they're explaining ANCOVA as regression, like to put the covariate in first, because what that does if you put them in first is say, what can our experimental effect explain over and above our covariate? As we'll see here, the significance test is going to be exactly the same as if we put them both in at one time, but I think it makes more conceptual sense to say what's the change in the amount of variance we can explain if we add our experimental effect in after the covariate. So to do that, we're going to say the covariate goes in first, and then we're going to put in our next block, we're going to put our experimental effect and our covariate in, and see what the change in the amount of variance we can explain. If our experimental effect can explain variance above and apart from our covariate, then we can say our experimental effect is significant. So to look at the change specifically, we're going to go to statistics. We're going to ask for R squared change, the amount of change in the variance we can explain. So with that, we're just going to continue and hit OK. That's going to give us a usual regression area, and we can see if we look at our overall effect, our final model with the covariate in the outcome is significant. Our second model with our independent variable included explains more variance than our model with just the covariate included. In terms of our R squared change, we see that our model with just our covariate in was just about significant, but what we look at with this, the change in R squared after our independent variable contributes about 40% unique variance, but that increase in variance is significant at 0.0001, and And let's go back and look at our individual ANCOVA. We see that this 28.371 is the same 28.371 that we see here. So this is all our effectiveness testing is. Can our effect explain more variance above and beyond the covariate? So we're saying it can, but I rather implied that I was going to use this regression example to show you why the homogeneity regression assumption is so important. If we look at the parameters that we use to predict our values, we see that, like I said, we get exactly the same significance value, and actually if we squared this T statistic, we'd get the same F statistic. So with two predictors, I could have just put them in one model and it would have had the same effect as including them hierarchically, because each T statistic tells us about the significance of an individual predictor. But I just wanted to do that for kind of ease of understanding. But for the rest of the time, what we're concerned with is these parameters, the parameters of the final model. They allow us to tell us how to predict our means. And in this context, we're not predicting an individual score. What the ANCOVA is doing is using these to adjust the means of our groups. So we see that here we had some means that were a little different to what our means were in our descriptor statistics. That was because we used this regression equation to calculate them. So if we, but why is the homogeneity regression assumption important? Well, the beta value, or the unstandardized regression coefficient, tells us about the relationship between our covariate and our outcome. Our estimate of that relationship is 1.442, but we see there's not an estimate of the relationship that's for different groups. It's one estimate overall, and that's the estimate we're going to be using to for the effect of our covariate. So if our relationship is different between our groups, then some groups it's not only a good adjustment because squeezing it all into one number doesn't accurately reflect the relationship. So that's conceptually why the homogeneity of regression assumptions is so important. I want to show you where those adjusted means actually come from now. So we can do that by looking at using that regression equation. Now, so we're going to use the regression equation as normal. Where do we get the x's, the value as well? 1.3 is the value for our 1.442 is the value for our covariate. But what do we times that by? Because we don't know the covariate for an individual person. Like I said before, we're working in terms of means now, in terms of working out those adjusted means. So we don't want to look at what the covariate is for an individual person. What we want to do is look at the mean of the covariate. And if we look here, it actually says somewhere here. The covariates appearing in the model are evaluated at the following values. So we 5.3, and where does that value come from? Well, it's the mean of the covariate. So the strength of our relationship of our covariate with our outcome is going to be times by the mean of our covariate. And just to prove that that is the mean of the covariate, let's get some descriptive statistics. So I'm going to minimize that for a second. I'm going to go analyze descriptives. I'm going to say we want descriptives on our covariate, and all I want to demonstrate my point is the mean in this case. And we see we get the same value of 5.3 as we got up here for the effect of our covariate. So it just in order to correct for the covariate, it just uses the mean of our covariate, ignoring what groups people are from. So that's another reason why the slopes have to be homogeneous. Well, how do we get from these or from these descriptive means to these adjusted means? Well, we just use that final equation. So we're gonna actually do this now. We're gonna start with our constant. So minus 5.873, I believe it was. Plus plus 1.442 times the mean of our covariate, which is 5.3. So wherever we go, we're going to get an objection of an adjustment of 1.7696. So again, that's another reason why this relationship has to be the same, because we're not accounting anywhere for the fact that the relationship might be different. Well, how do we work out the means for our individual groups? Well, we just supplement in with the code that we gave for that group. So the effect of our experimental effect has a regression weight of 6.688. So we're just going to times that by the whatever group we're in. So in this case, if I go back here and I turn off value labels, the no redirect group has a value of 1 and the redirect group has a value of 2. So we're just going to supplement those values in. So if I do the control group first, so plus 6.688 times 1, because remember that's the number we assigned to no redirect group. Here, everyone's a no redirect has a value of 1. We get 8.4576, and if we go back to our output here, we see that our adjusted mean for our first group is indeed 8.456, which is the same as we got here. So, and our second group restorer gave a value of 2. So if we say that this time our variable is 2, we end up with 15.1456, which is basically the same as the model calculated for our redirect group. So that was giving you a bit of a theory of ANCOVA as regression, and just how to conduct ANCOVA in general. So hope you enjoyed this video. Sorry it was long, but I wanted to explain that thoroughly, and I'll see you in the next one. Bye bye.